In today's lecture, I'm going to show you how F equals ma breaks down and why you need special relativity and ultimately general relativity to show that you can never cross the speed of light. Welcome to today's episode of General Relativity. I'm your host, Bari, Brown University physics grad student. Let's get started. Let's start with something we all learned in high school Regents physics, the kinematics equations. The kinematics equations tell us how an object moves if it has constant acceleration. So remember that according to the kinematics equation, your final velocity for an object is your initial velocity plus at. Now let's say the object starts from rest. If the object starts from rest, then we simply have Vf, the final velocity, is a times t. So if we draw an at graph, a graph of the acceleration versus time, here's how that would look like for a constantly accelerating object. Here is time, and here is acceleration. And for a constantly accelerating object, the acceleration is just a straight, constant horizontal line. Now, what about the velocity? Well, the velocity is also very simple. The velocity, according to this equation, is simply linear. So here's the velocity of a constantly accelerating object. And what about the position? Well, according to our last kinematic equation, the position of an object that's constantly accelerating is distance is equal to 1/2 at squared. So that gives us a parabola like this. But now you can ask a simple question. You say, according to Einstein's special relativity, no object can move faster than light. This is not possible. But if you look at this graph, you can see very simply that after a certain amount of time, if you're accelerating fast enough, then you will cross the speed barrier of the universe. You will cross the speed of light. So Newton's equations, the kinematics equations, have a very obvious problem. And the problem is very easy to see even in Newton's, even in Vf is equal to Vi plus At. Simply put, if Vf is equal to C, and let's say A is G, then the amount of time you need to exceed the speed of light is simply C over G. So that means even if you have a ball that's falling, that's in free fall to the ground, that ball, after C over G seconds, is going to be moving faster than the speed of light. So clearly there's something very elementary that goes broke in Newton's second law, in the kinematics equations. Now the question becomes, how does Einstein's special theory of relativity fix this? How does Einstein's theory fix this d is equal to 1/2 at squared and v is equal to vi plus at to account for the speed limit of the universe? And the answer is this. Einstein's special relativity shows us that the velocity of a constantly accelerating object actually looks like this. It looks like a kind of logarithmic curve. And if you increase the acceleration, let's say you double the acceleration from here to here, then your curve will simply approach the speed of light faster, like this. So that's the basic idea behind what happens in special relativity. And the position graph goes from a parabola that goes as 1/2 at squared. That parabola now becomes a hyperbola. And that hyperbola looks something like this. So that hyperbola looks something like this. And that hyperbola has asymptotes as follows. So here are the asymptotes of our hyperbola. So in summary, according to Einstein's special theory of relativity, the velocity of a constantly accelerating object becomes this logarithmic function, and the position becomes, instead of a parabola, it becomes a hyperbola. Now my goal is to prove this. So let's go ahead and prove everything that I just said. So I'm going to erase everything that we've come to know from Newtonian mechanics, and we're going to derive the special relativistic version of these statements for a constantly accelerating object. So the first thing we're going to do is start with an object that's moving at a constant acceleration in special relativity. So let's take a marker that's actually working. So here's an object, and let's say the object has some constant acceleration a. Now in special relativity, we describe the acceleration of an object using a 4 vector. And so that 4 vector I call a mu. and it has components a0, a1, a2, and a3. Likewise, we describe the velocity of a relativistic object using a velocity 4 vector, u to the mu, that has components u0, u1, u2, u3. Now, it is a fact that u mu dotted with a mu must equal 0. This is a key fact in special relativity, that the velocity and the acceleration vectors must be perpendicular. One way you can easily gain intuition for this is that if you have an object moving in a circle, then the velocity vector of the object is tangential to its path, whereas the acceleration vector points inward to the circle, and so indeed you have a perpendicular relationship between the velocity and the acceleration. So we're going to use this relationship to figure out what the acceleration and velocity looks like for a constantly accelerating object in special relativity. Now, let's say our object here is accelerating with some velocity, accelerating with some constant acceleration alpha in just the x direction. So that means our acceleration vector won't have any components in the y or z direction, and neither will our velocity, because we're not accelerating in the y or z directions. So now let's just write down what we know about our velocity 4 vector. Our velocity 4 vector is simply the time derivative with respect to proper time of our position 4 vector, where our position 4 vector x mu is simply the coordinate time t, and then our position coordinates x, y, z. So here we have dx mu d tau, or I can rewrite this as dx mu dt dt d tau. But of course, I know dt d tau by the Lorentz transformations simply becomes the gamma factor. And so what does that mean if not u mu is equal to gamma times dx mu d tau? And so actually I shouldn't put a vector here, it's not a vector. And so remember that x mu is t comma x. So this becomes 1 comma v. So this is the velocity 4 vector in special relativity. So now that we have the velocity 4 vector, okay, we know what the velocity 4 vector looks like, we should be able to get the acceleration 4 vector by imposing this condition. So according to this condition that the velocity and acceleration 4 vectors are perpendicular, we have that u0, a0 plus u1, a1 is equal to 0. Okay, well, very well. Now let's replace these by their respective components. u0 is simply gamma a0 plus u1 is simply gamma v, gamma v. Now, of course, in our case, we simply have gamma 1 v 0 0 because there is no y or z component for our velocity 4 vector, because our object is not accelerating in any direction except the x direction. And so we have this plus 0 is equal to 0. And let me be careful here. So this, let's be careful over here. So we had u0 as gamma times a0, and then u1 is gamma times v, and then times a1. That's equal to 0. Now let's divide through by gamma, and so we find that a0, the 0th component of the acceleration 4 vector, is v times a1. Now this is going to come in handy in just a sec, as soon as we figure out what a1 is. Now, we know that the acceleration 4 vector is simply the second derivative of the position 4 vector, right? Well, we can also write that as the first derivative of the velocity 4 vector with respect to proper time. But wait a second, I can also break this down in terms of coordinate time as follows, just like I did over here. But now, if I break this down as d mu du divided by d tau, I can break this down as du dt, dt d tau, but dt d tau is once again the gamma factor, right? And so I can write that the first component of the acceleration 4 vector, this first component, is simply going to be gamma, so this gamma, times du1 dt. But du1 dt, well, isn't that just the acceleration of my object in the x direction? So this is simply gamma times alpha, okay? So that means a to the 1 is just gamma times alpha. So now I can find that a to the 0, the 0th component of the acceleration 4 vector, is simply v times gamma alpha. Okay, great. So now we know what our acceleration 4 vector is. Let's write it down in red to emphasize that the acceleration 4 vector is the 0th component, which is v. Actually, let's write the gamma out front, or let's write the alpha out front. So alpha v gamma, comma, a to the 1, which is gamma alpha or gamma, and then everything else is 0. Okay, so now notice this is our a mu for vector. Our u mu for velocity is gamma and gamma v, and then 0 comma 0, right? So now notice that this first component of the acceleration 4 vector is simply the second component of the velocity 4 vector. So this right here is u to the 1. And likewise, this second component of the acceleration 4 vector is the first component of the velocity 4 vector, u0. So in other words, now I can set up some differential equations. So I can say that, let's come over here. So I can say now that, oopsie daisies, we have this acceleration 4 vector, so a0 is equal to alpha times u1, and a1 is equal to alpha times u0. But now, of course, I can leverage the fact that alpha is the acceleration 4 vector is simply the derivative of the velocity 4 vector to write these as differential equations in the 4 velocity. So if a0 is equal to alpha u1, what does that tell me? Well, a0 is simply d u0 d tau. This is alpha u1. Now, u1, I know what u1 is. u1 is simply this one, gamma v. So let's write this as gamma, oopsie daisies, gamma v. Now, u0, du0 d tau, what is that? Well, I know what du0 is. That's simply gamma, but that's not going to help us here, okay? So instead, I'm going to write this as du0 dt d tau. Okay, this is alpha gamma v. Now dt d tau is gamma. Okay, so dt d tau is gamma, and now I can cancel out gamma from both sides. So now I'm simply left with something much simpler, which is du dt is equal to alpha v. Now, hang on a second. Let's see if I'm doing this correctly. So this is good. Let's also write down the differential equation for this one. A1 is equal to alpha u0. So I'm going to write that over here. A1 is equal to alpha u0. Right. So let's see if that makes sense. Alpha u0, alpha u1. So A1 is du1 d tau, and this is alpha. Is that what A1 is? Yeah, that's good. And this is alpha u0. u0 is, of course, gamma. Now I can write this as du1 dt d tau is equal to alpha gamma. dt d tau is gamma. And now I can cancel out gamma from both sides. And so I'm left with du1 dt. So du1 dt is equal to alpha. Okay, great. So now let's erase all of this. And now we can take this and solve for u1. Let's integrate both sides with respect to t here. So I have du1 dt and alpha dt. Okay, integrating both sides with respect to time, coordinate time, gives us u1 is simply alpha t. Now u1, of course, do I know what u1 is? u1 is simply gamma v. Okay, so let's replace u1 by gamma v. So now remember, we're solving for the velocity, right? So the velocity is alpha t divided by gamma. Now, this here is incriminating because I know what gamma is, right? So this here is going to be velocity is alpha t. Remember that gamma is the gamma factor, which is given by 1 over square root of 1 minus v squared over c squared. Now, hang on, my gamma should be, I think I might have made a silly mistake here. Let's slow down here. So this is du1 dt. Okay, so that gives me, let's see, I've got my factor of gammas canceling out here. My factor of gamma is canceling out here. I've got only alpha on the right-hand side, du1 dt. And so I've got du1 dt, integrate both sides with respect to t. So I've got just u1, okay? And u1 is simply gamma v here. So gamma v, okay, this looks to be okay. So bottom line is that v should be alpha t over square root of 1 minus v squared. V squared over c squared, right. And okay, good. Okay, I was worried that I had made a mistake somewhere, but I'm actually making all the right things. So gamma, of course, is 1 over 1 minus v squared, so that's what I have on the left side. Okay, remember I want to solve for my velocity as a function of time, so let's square both sides. So I've got v squared over 1 minus v squared is equal to alpha squared t squared. Now we're rolling. Let's move here to the right-hand side and solve for the velocity as a function of time and show you that the velocity cannot exceed the speed of light. And so it obeys the special theory of relativity. So bringing it over here, we find that v squared is alpha squared t squared minus v squared alpha squared t squared. Move that to the left-hand side. V squared times 1 plus alpha squared t squared is equal to alpha squared t squared. So that v squared, the velocity, is simply alpha squared t squared divided by 1 plus alpha squared t squared. Square root both sides. We find that the velocity is equal to alpha t. The velocity as a function of time is alpha t divided by square root of 1 plus alpha squared t squared. And so this right here is equal to our velocity. And this right here is a logistic function or a logarithmic function. And if you plot it out, this is how it looks like. So let me plot out our new special relativistic version of velocity. So here is v, here is t. Our original version of velocity, our original velocity function for a constantly accelerating object looks just like this. But now we have a speed limit, we have a speed barrier, and that speed barrier is the speed of light, which is c or minus c. And so now our graph looks like this. Looks like a logistic function, just like that. And now we can actually solve for position as well from this formula. So let's go ahead and solve for the position of an object that's constantly accelerating in special relativity and show that it is indeed a hyperbola. By the way, if you want to get some intuition for this equation, it's actually very easy to do so using a Taylor approximation. So if I do a Taylor approximation on the bottom square root, I get v of t is equal to alpha t times 1 plus alpha squared t squared 2. Now this is to the minus half. So if I approximate this as alpha t, 1 minus a half alpha squared t squared, then I get this. And so this gives me about alpha t minus 1 half alpha cubed t cubed. And so that gives you some kind of a vague idea of what this looks like for small t. For small t, then it grows like a cubic. And that's exactly what you expect a logistic function to do at small t. But at large t, it tapers out like so. And you can see that very clearly over here. At large t, you can see that this denominator is going to prevent the numerator from exploding because they both have the same power of t, right? So you won't diverge to any large values larger than c. But anyway, so now let's show that the position function for this constantly accelerating object is indeed a hyperbola in special relativity. So I've got my velocity, but what is velocity if not dx dt? And this is coordinate time. It's not your proper time. Otherwise, I wouldn't be able to do this. So this is dx dt is alpha t divided by 1 plus alpha squared t squared. Now this is just an integration problem, isn't it? So this is x of t is the integral from 0 to t of alpha t prime divided by square root of 1 plus alpha squared t prime squared dt prime. Now I'm going to use some clever u substitutions to show that this is a hyperbola. So I'm going to make u equal to my denominator, which in this case is 1 plus alpha squared t prime squared. That tells me that du is 2 alpha t prime and then times alpha and then dt prime. And so if I solve for dt prime, I get that du divided by 2 alpha times alpha t prime is equal to dt prime. And so now that makes my entire denominator here useless. It's just u. And so this gives me that x of t is the integral from 0 to t of alpha t prime, that's my numerator here, divided by, and then I can just write the denominator as u to the half. And then instead of dt prime, I have du divided by 2 alpha squared t prime. Now I've got some things canceling out on the top and bottom. I've got a factor of t prime that cancels out, and a factor of alpha that cancels out. And so I'm left with x of t, my position function, is 1 over 2 alpha, and then I have the integral of u to the minus 1/2 du from 0. Well, my integral limits will change, but we'll see that shortly. So now if I integrate this, this is simply what? 2 u to the half, and then 1 over 2 alpha, 2 and half cancel. So I'm left with my position function as 1 over alpha times u to the half, where u is given by this substitution. So let's plug that back in. So I have 1 over alpha times 1 plus alpha squared t prime squared, where t prime goes from 0 to t. And so that means my position function, x of t, is equal to 1 over alpha times 1 plus alpha squared t squared. Now if I just go through the math here, then this is simply going to be, now is this supposed to be, yes, that's good. So I guess I'm talking to myself at this point. So x of t, my position function over here, can you see this, is 1 over alpha and plus alpha t squared. Okay, so now something is wrong. There should be some kind of a square root here. Oh, there is a square root. Here's my square root. So this is u to the 1/2. So there should be a square root right here. Okay, great. So now that I've taken into account the square root, let's square both sides. I get that x squared is 1 over alpha squared times 1 plus alpha squared t squared. Okay, so now let's just cross the i's, dot the t's, or dot the i's and cross the t's, something like that. So I have x squared is equal to 1 over alpha squared plus t squared. And so now, this is almost a joke. Here you go, here's your parabola. This is actually why the space-time interval is defined the way it is, as time with a minus sign and space with a plus sign. And so now if I plot this out, here's how that looks like. Here is position on the x-axis, time on the y-axis, bada bing, bada boom. Here is your hyperbola. And this hyperbola has asymptotes, where the asymptotes are the roll lines of a null geodesic, the roll lines of a photon. So this is v equals c, and this hyperbola here is given by x squared minus t squared is 1 over alpha squared, where alpha is your proper acceleration for your observer. So thank you for watching, folks. I'll see you in the next one.